So in this session we are going to discuss about verification of ANSYS results with the hand calculations. Before that, we have already checked with the boundary conditions on deformation matches, equilibrium also satisfied, and the ANSYS results are also independent of mesh. Now last part, we are checking a comparison with the hand calculation of stress. Before that, I just want to highlight that if you add the beam tool, you will not get the results because they're subjected to transverse loading, right? So there is no direct stress and combined stress, direct plus bending stress will be there. As direct stress component is missing, so we will not going to check this in the beam tool, right? We already have a shear force and bending moment diagram for this kind of problem beams. Next, let's compare with the hand calculation. So this is a given information. We have W12 by 35 beam, length is 11.5 feet, E is 30,000 KSI, and subjected to 35 pound per feet of load. First step is to understand the equilibrium condition for entire beam, and we'll express one in another term with the taking the reaction at one end, right? So if we'll balance the forces in y, okay, then so what we are doing here, we are doing summation of Fy equals to 0. So Ra on one side and other side here Q into L, right? So that let consider this to be act at a point load at L by 2. So the force, if we'll convert this UDL into point load, then it will be Q into L, right? So the force Ra at this end, Ra, right here it will be Rb, right? So Q into L minus Rb, right? So this is this on the right hand side we are taking positive and this as negative. So this summation of Fy equals to 0. Moment about A equals to 0. In that we are going to take this moment about A. So here it will be Q into L by 2. That's QL square by 2 minus Rb into L, right? So here we are taking clockwise as a positive and here anti-clockwise as a negative direction for the moments. So we have made two equilibrium equation, moment is 0 and force equals to 0. Now let's consider a distance x away from some fixed support. So let's take some distance x away from this fixed support. So movement about that point will be equals to Ra into x minus Ma minus Q into x square by 2, right? So that will be the force which will get at moment force at this end, right? Moment about x. So it will be this Ra force into this distance, Ra into x. We are taking the left hand side values, so Ra into x, this part UDL, so its magnitude is Q and it will act at, let me consider its point load, so it will be Q into x will act at x by 2, so it will be Q x square by 2, and this moment which we have got from the last part, Ma. So this is moment at point x. On substituting the value of above, we got Ra equals to QL minus Rb. So we have written QL minus Rb into this x comes here. Q, then moment about A, that's a QL square plus RBL, right? And minus Qx square by 2. So this is a moment at x. Now the second order differential equation for deflection curves, if we'll differentiate this for ei into dv by dx, right? So this is a moment equation. If you remember our Gaussian equation lecture, which we have understood that moment equals to ei into dv by dx. So that this is that. So here we are, this equation will become a second order differential equation for movement, and if we are integrated once, we will get a slope, and if we integrate it twice, we'll get a deflection, right? So for first integration, we'll get slope, and if we'll double integrate it, we'll get a deflection. This. So this QLX will become QX square by 2 minus RBX square by 2. This QLX square, this constant term, integration of this constant will be x. Here also it is a constant term, RBL into integration of 1 dx is equal to x minus q. X square integration is x cube into by 3. So it will be 2 into 3 is equal to 6 plus c1 constant of integration. If we'll double integrate this, we'll get QL x cube by 6 minus RB x cube by 6 plus QL square x square by 4 plus RBL x square by 2 minus QX raised to 4 upon 24 plus C1x plus C2, right? So this will get a deflection equation, and this deflection equation here we don't know C1, C2 and this RB, right? So for that, if we'll apply the boundary condition at x equals to 0, right? The dv by dx at x equals to 0 is 0, right? So what is dv by dx? dv by dx is slope, right? So it's a fixed end, so slope will be 0 at this point. So if we'll put into that equation, we'll get C1 equals to 0, right? We'll get C1 equals to 0, right? So here everywhere it's x term, so 0 multiply with this, all things, it will become 0. So C1 will be eventually become 0. Next is a deflection, right? So deflection at this point, fixed support will be equals to also 0. So V at x equals to 0 is equal to 0. So in C2 will also become 0 if we'll put x equals to 0 in this term, and C1 is also 0, so this full term becomes 0. So C2 will also comes to be 0 in this equation. Now if we'll simplify this term, deflection term, okay, then we will get 3QL by 8 in terms of RB. Okay, so 3QL by 8, 3 into Q is 35 pound per feet into length is 11.5 divided by 8, we get the 0.151 kips. So that is 151 pound force. Okay, so let's check with the right. So here we are at fixed support. Let me find out the reaction at B point. B point is this displacement point. Okay, so Ry is 151.51 pound force, and what is that matching with our hand calculation also, 151 pound force, right? Kilo inch pound, right? Kilo pound, sorry. Kip says kilo pounds. Then at the A end, which is a fixed support, at fixed support it's 5QL by 8, right? So we'll get 0.252 kips, and here also we are getting 251 pound force. Here we are getting 252 pound force, so there's 1 pound difference we are getting, but that's very close. The moment about A, we are getting here 570 pound per feet, that's 0.57 kip feet, 570 pound per feet at the moment about A. So let's see the shear force bending moment diagram here. Yeah, so here also we are getting around 572 pound feet as the maximum bending moment at A point, fixed point, right? That's what also matches with our analytical result, which we have found by hand calculation. The bending moment is 0, will be at L by 4. So that also we can check. Let me just pull up this graph. And let me just go right side table data. So here the green one is our bending moment. So if you'll see that the 0 bending moment is at 2.875 feet in answers also, right? So that is what you can drag and drop this at location. I just clicked on this location. So it's 2.875 feet location. We are getting this bending moment to be 0. So that is also what matching with our analytical solution. So we have completed all the verification stages. We have compared with the hand calculations also. Comparison hand calculation. So we've done all the part. So you can now do the assignment, and if you have any query, just check FAQ section or just write down in our community group for the question. We'll revert you as quick as possible. Thank you. So next we are going to see the lab 5 on natural frequency analysis.